positive that way. So that I've already taken account of that as a negative sign. So don't plug in the negative when you plug in numbers in. Right? It's already been taken into account. Any other questions? I may be able to, but I don't do something about it. All right, so question 5, I'm not going to do this problem, but the question says this. It says, we're going to have the same scenario as this problem, except we're going to change the message around. And the question says, what angle would make the whole system remain at rest, or move at constant velocity? Either remain at rest or move at constant velocity means that acceleration is 0. So what you're going to want to do in this case is you're going to want to solve for theta, assuming that acceleration is 0. And you'll see something interesting. And you'll notice that I changed the masses. I changed the masses so that M2 is heavier than M1. If you try to make M1 heavier than M2, no matter what angle you choose, it will never remain at rest. And I can show them to you by just looking at this formula. If I want this thing to be at rest, so let's say acceleration equals 0. This is kind of what it's over 5. If I have set acceleration equals 0, it's a simple equation to solve. I just set that equals 0. This cancels that cancels. All I'm going to have is M2 sine theta minus M1 equals 0. Which tells me that sine theta equals M1 divided by M2. That's for A equals 0. So if you want this equation to be satisfied, what's the biggest number sine can be? Sine of some number, what's the biggest it can be? 1. The smallest it can be is negative. Well, these are all positive. So the biggest it can be is 1. Which means that if I have M1 bigger than M2, there's no way I can make that equation satisfied. So for this thing to actually remain at rest, you have to have the mass on the incline heavier than the mass it's hanging. Because gravity only affects it to some extent. Its gravitational pulling it that way, which is not taking into account that the whole gravity pulls down. It's kind of some component of it. So gravity kind of acts on this a little less than it acts on this, which is why you get heavier mass to counteract that. Okay? Let me just go over the problems. One or two of the very nice problems. Okay, so this is a good problem. This is problem number 29 in chapter 5. Again, this is a sign, so if you are stuck in a solution, you can always go back and look at this solution online. The question says, a firefighter who weighs 712 newtons is sliding down a vertical pole with an acceleration of 3 meters per second squared. So, I don't know if this still happens in real life. They have that like pole where firefighters slide down when they want to fight a fire. I don't know if it's the case, but imagine that he's going down a pole from the second floor to the first floor. He's going down. And he's not going to go down like as if he just jumped down, because that would probably break his leg. So he goes on a pole to slow himself down. Because he's doing that, his acceleration is only 3, not 10. And the question is, what is the magnitude and direction of the vertical force on the firefighter from the pole? So I just draw a picture. This guy's going down. His acceleration is 3 meters per second squared. And the question says, what is the direction and magnitude of the force from the pole, force on the firefighter from the pole? So the force on firefighter from the pole. You know there's going to be a force on it, because if there was no force, he would just be going down at 10 meters per second squared. There's got to be some force changing his acceleration. Yeah, it's a frictional force. And I'm not going to talk about really how friction is related to normal force. This is just going to be a force, this pulsing force. So again, draw a free body diagram and label all the forces that are on this thing. He's going to have his weight, so this is the firefighter. His weight's pulling him down. There's some other force that's going to be pulling him up. And it may not be obvious to you which direction this force points in, because frictional forces can be notoriously tricky to see which direction they're going. So I'm just going to call it off. And if that's not right, we're going to get some negative numbers at that point. And we'll know what point's there. But let's just call it off. I'll call it force in the pole. And it's a frictional force, but really all that matters is that it's some force pulling him up, whether or not it's frictional. And if you just solve this equation, you can do the second law. You get Fy equals MAY. This is a pretty straightforward one. And I'm going to make my coordinate system. That's the y direction. So in the positive direction, I have F pole. In the negative direction, I have W. And then what I put on the right side, we're going to have mass times acceleration. Now that acceleration is not g, keep that in mind. It's giving you this acceleration as -3. It's -3 here. That's actually his acceleration. That would be his actual acceleration. It's related to gravity, but it's not gravity. There's other forces. And if you solve this, you're just going to have the force of the pole upon this guy is -3 times m plus w, which is -3 times m plus g times m, which is g minus c. No. The question was, in this situation, if you plug in -10 for g, don't ever plug in -10 for g. Because you're always drawing the vector down, and that negative is there. So always plug in for g. I want you to do a related problem. A related problem. Yeah, okay. So are there any questions on that problem? That's a straightforward one. But again, just make sure you're using acceleration here, not resonance. This is good. All right, so let me do one from the homework again. I'll get over yeah, let me go to 7, because that's a static one. So number 7 has this picture of these like ball thing and suspended. It's a lot of Okay, the question, it says this. The whole picture below is some mass is suspended, it's not accelerating. Find the tension T1. This is T1, T2, T3. It wants to know the tension of that string. I mean, now I know we discussed how like the tension from these two strings that are connected are the same, every one string. But these are like, there's two strings connected to this one string. So the tension in all these ones will be different. Because there's a lot of them connected in one spot, not just one string. So the fact that it's not here means that you're going to have different forces pulling on it. You want to use that to help you along with the problem. So this is a little strange that there's actually two free bodies in this system. One is the block at the bottom, and then one is the knot. And the reason I'm saying the knot is a free body is because it has forces pulling in all directions. So we can use that to find out how to roll it. So let's draw those two free bodies. The block is actually pretty straightforward. It just has weight pulling down and tension pulling up, tension 3 pulling up. And then the knot has it has this going on here. It has T1, T2, and T3 pulling down. We haven't really defined a coordinate system on the right-hand side. There's a couple ways to do it. You could, well, actually, if you look at the problem, you can probably do in your head real quick, what is this angle right here? It's 90 because these add up to 90. So this is a right angle. So it might make sense to actually use this as your coordinate system. Because now two of your
Solve the
your
screen.
forces are already in the right direction. They're along
Is
here.
it easier to put it like this because otherwise T8 is all T3 in a components and resolving T3 in components is much tougher than resolving these
Okay,
two
so you're saying maybe
components.
this would be easier? Okay.
You got to move it over.
Maybe you could do it like that easier. This is how I did it. There's two ways to do it. So I'll do it this way because I did run down my notes. This way should in theory be the same thing. I think you should be able to find that.
How do you resolve
Let me try to do both methods. So. Again, there's two ways to do this problem. Because nothing's moving, it's a little, you have a little more freedom in choosing your coordinate axis. If something was accelerating, you want to choose the acceleration in the direction or the direction expected to accelerate. Here, nothing's moving, so you can kind of choose either one. Let me try this system first. And if we just solve these equations, then this one is straightforward. This is sum in the y direction equals 0, because there's no acceleration in the problem. You can have T3 minus W equals 0, so T3 equals W. But the question is asking for T1. So you have to use that in your next equation to solve for T1. Now, if I just bring this up in components, according to my axes here, I have only one of these forces are in the x and y direction. The other two are broken up into space, so I have to draw these components. Let me draw that picture a little bigger. So that's T1, and this is T2. And so this guy, so I think this thing turned off, so I have to look. So you have T2 that's pointing in this oblique direction, then T1 is pointing in that oblique direction. And you want to break it up into these components. If you write it like that, then just use your trigonometry and figure out what these angles are. It shouldn't be too hard. And if you look at what you have on the top,
It's going to be.
so this angle I think is 50. This angle has to be 40. And then this angle likewise is 40, so this has to be 50. So there's some pretty straightforward trick you can use to find out what these components are. If that's the angle you're using, this guy is going to be T2 cosine of 40. See that? Because it's the adjacent side. This is T2 sine of 40. Likewise, this is T2 cosine of 50. This is T2 cosine of, sorry, sine of 50. And now you can just kind of add up all these forces in the x and y directions, and the accelerations are 0, so it's going to be straightforward. So if I do the x direction, I have the sum of the forces in the x direction equals this x is going positive because my coordinate axis is like labeled like this. So it's T2 sine 40 minus T2 sine 50.
Is it T1?
Thank you. Oh yeah, thank you. T1. Sorry. This is T1 right here. Minus T1 sine 50. And then in the y direction, so I also have this T3 going down here like that. So in the y direction I have T2 cosine 40 going up, T1 cosine 50 going up, and T3 going down. And you know what T3 is? You can just plug in the weight to find T3. And so I guess to solve this equation, what you probably do is solve one of these for T1 and plug it in the first equation. And now you have an equation only in terms of T2. So you can solve for T2. Something like that. Solving it is just kind of manipulating it algebraically and just plugging it in. Any questions on that problem? Let me do a friction problem before we leave. There's nobody after us, I think, so I'm going to go a little over if you want to hang around. If you have to go, the time is actually up.
Virat, could you have drawn the angles up on top instead of the bottom?
Meaning like this?
Like if they go straight up? Well, the way that I was explained in the physics lab was they said the T2? T2's force is more than T1's. So that meant, and he said that the horizontals, they have to be equal.
Yeah, that's it.
Okay.
All right, I'm gonna do number 9. We need to number chapter 6, number 5, because I want to get us kind of started with friction with some easier friction problems. This friction can be kind of a tricky force because it's not constant. Alright, so the thing about friction is that it kind of depends. First of all, it depends if the object is moving versus stationary. And then it also depends on how much force you're pushing it with if it's stationary. So let me give you guys a couple of just examples here. Alright, so I want you to imagine these situations. Imagine that you have a block on a surface, and the surface is now rough, so there's going to be friction between the block and the surface. And that friction is going to prevent you from actually accelerating the block. So imagine that in the first case you have a force of 3 newtons pushing that block to the right, and then the second case you now increase the force to 5, and the last case you increase it to 8. And you can just imagine once later I have like my mug here. If I push it with 3 newtons, I just kind of barely touch it. Let's say it's a very small force, and it's not accelerating, right? But I'm going to push it a little harder now. Imagine just like I'm really pushing it. I know it's kind of imagine like really pushing the book, like a little more force. Maybe I can pretend I'm pushing this actually. So right now I'm just pushing with a little bit of force. Okay, and there's friction between this thing and the ground. It's actually stuck to it, so there's a lot of friction. So it's not going to move. And then now I push it even harder. It's still not moving. So this is the second case. And I can push it even harder and it's still not moving. In each case, there's a frictional force that's opposing my force. So I'm going to draw that this way. But what's critical here is that in each case, the object in question is not moving. And that means we can solve for the frictional force very simply because acceleration equals 0. So in each one of these cases, I'm going to have F minus FF equals 0. Because it's not accelerating. If I just solve those each time, I'm going to have FF here equals 3. FF equals 5, and FF equals 8. So what that means is, depending on how hard you push, the frictional force has to be equal and opposite to your push. If it's not moving, because it's got to prevent it from accelerating. So that frictional force is actually pushing back. And that force has to be equal to what I'm pushing with. Now, this situation changes when you actually have something starting to move. So the thing about frictional forces is that they can only work up to a certain point. Because they're friction, they don't work forever. For example, this book, I can push a little bit, but at some point it starts moving because the frictional force isn't enough to keep it from not moving. The max number that this can be is, it's called the coefficient of static friction times the normal force. So this is the greatest it can be. In this case, it's going to be 3. In this case, it's 5. In this case, it's 8. But once I get to this number, whatever that number may be, it's going to start moving. It's no longer going to be equal and opposite. You're going to start moving the book or whatever. Now the thing about it is that once it actually starts to move, it's a little tricky because this is what gets it moving. But then once it starts to move, it moves with a different force. So once it's moving, the frictional force is a constant number. It's mu k times Fn. I think I actually have Fn on here. I can show you how to do that. Yeah, let me put it on this one. This is a really nice Fn. You can choose a different object in this thing. So you see how this guy's pushing this file cabinet? You see how he's pushing with this blue force and the friction force is the red one? And it's equal opposite to it because it's not moving. And at some point he's strong enough and he can actually start moving it, I think. Perhaps. So see now the applied force is greater than the friction force, it's going to accelerate. But no, if I even make a bigger one, the friction force will be the same. I'm changing this around, it's still the same. So once it's moving, it's this mu k times Fn. But to get it up there, the highest you can push it is the one that he was accelerating it with, the one he was pushing against. Let's say, for example, I have maybe something this one's a little lighter. This textbook. Now he's above it. See his friction force? You see the red one's not changing? Look at it quickly, sorry. This thing even has sound too. Maybe this dog. So notice what happens. Once it's above, I'm going to increase the force. The red one's not changing. The friction force is constant. But to get it to that point, you have to actually overcome the force, the static friction force. So going back to the problem we had here, the problem is a little tricky because you have to imagine how much force, you have to figure out how much of the max force you can push it with before it starts to move. And then after that, the friction force is easy. So let's do number 5 in chapter 6. This is a good illustration of how this works. All right, so this one says, a 2-kilogram block is initially at rest on a horizontal surface, and there's an applied force of 6 newtons being applied to it to the right. There's also a vertical force that's pulling it up, and that we're going to assign different numbers to that force. The coefficient of friction are these numbers: μs equals 0.4 and mu k equals 0.25. It's typical. Usually, to get it moving requires more force than the actual force once it starts moving. So this μs will always be bigger than mu k, pretty much. The question says, find the magnitude of the frictional force if the magnitude of P is, and it gives you a couple situations. First, when P is 8 newtons, B when P is 10 newtons, and then C when P is 12 newtons. So it says, imagine that somebody's like trying to push this block and somebody else is pulling it up, and he's changing how hard he pulls it up. For those 3 situations, find out what the frictional force will be. Okay. So you can't just plug in formulas blindly. You have to think about whether it's reached the max capacity for friction. So in this problem, let me just draw the free body diagram. The force is this direction, and he's pulling up with P. There's also normal force going up, and there's weight coming down. And there's going to be a friction force pointing opposite to the direction of the applied force. That's going to go that way. So let's just do the Newton's second law for this first case. in the y direction, I'm going to have, let me do the x direction. The x direction is f minus ff, sorry, I forgot to make that point, equals, and we're saying it's not, well, we're actually not sure if it's accelerating, so just leave this like this. Now, in the y direction, that's not accelerating, and that's just p plus fn minus w. And I think we, P is given, and then W is given, because we know the mass. The mass is 2.5 kilograms. So we can find this out. This should be 0. I'm going to go ahead and give you the numbers for this, because I want to illustrate what's happening. So after, when you plug in these numbers, this is 2.5 times 9.8. This is 8 for the first case. This is A. This will be 2.5 times 9.8 minus P, which is 8, and that number will be 16.5 newtons. Okay? So the normal force is 16.5 newtons. Using the normal force, we can immediately calculate what the maximum frictional force will be. The max frictional force, let me say max static frictional force. This is the force you need to actually get it moving. You have to overcome this one to get it moving. Is going to be mu s times Fn. It's a static friction coefficient times this normal force, which is 0.4 times 16.5, about 0.4 or so. No, 6.6. Yeah, 6.6. Okay? What that means is that if I push with anything less than that, the thing's not going to move. However, if I push with more than that, it's going to move. In this case, what's my how much am I pushing with? 6, right? Up here it says I'm pushing with 6 newtons. So will this thing move?
No.
No. Which means, what is the actual frictional force have to be?
Greater than 6.
That's a good question. So let me make this a quick question. If you have a quick, go ahead and take it out. So the question is, frictional force equals A, 6.6, B, less than 6.6, C, greater than 6.6. And I think it's this frequency AA. So what do you think the frictional force would be? Sorry. 6.6, less than 6.6, or greater than 6.6? We just found the max static friction is this much. It's pushing with 6. Okay, I'm going to stop the results now. Here's what the results are. So most people said it's less than 6.6, and then Unico amount said it's either equal to or greater than. And somebody who said it's B, the majority, want to explain their answer, how they got that? Yarmi?
When you want to move, like, toward the side, the force is 6, right? So, you want it less than 6 newtons because you want to overcome that friction. So you want something that's less than 6.
Okay, so you want to overcome the friction. So you're saying that the friction force is less than 6.6.
Yeah.
What is the actual number for the friction force? Or you're not sure? Okay, so it's less than 6.6, you said, because you want to overcome the 6.6. Does somebody know what the actual number for the friction force is in this case? What your name?
Sure.
Okay.
It's 6
How come?
because the friction is only as much as how much you're pushing in is giving you that friction, and then once you succumb to friction, then
Okay, you said up to a certain point, it's only as much as you push it with, which is exactly right. You're pushing with 6, but you haven't reached this breaking limit yet. You haven't reached 6.6, so until you reach that, it's just going to be whatever you're pushing with. So the actual frictional force equals 6 newtons. Okay? Until you get to that point. So the answer was B, it was less, but the actual number is 6 newtons. Now, however, if your frictional force, your max frictional force is less than 6, then it's going to be a different situation. So let's look at, let's go on to C actually. So if I take us a step further and plug in, when I have C equals 12 newtons, when I have P equals 12 newtons, run back to this formula. So if I do part C, I'll skip B, let's do part C. So again, we have to find out the normal force. The normal force equals W minus Fn, sorry, equals W minus P, which is 2.5 times 9.8. In this case, P is 12. So this number ends up being 12.5 newtons. And if you plug that into the max friction, you get mu s times Fn, which is 12.5 times 0.4, which is 5. So 0.4 times 12.5, and that's just 5. Now notice that the max frictional force this thing can handle is only 5 newtons. However, how much we're pushing it with is still 6. So we're still pushing it with 6 newtons here. Okay? So it'll actually start accelerating. But what's a little tricky about this is now that you know it's accelerating, the frictional force is not this number. This just gives you an indication of if it will or will not accelerate. The actual frictional force is going to be, so this tells you accelerates. And the actual frictional force equals mu k times Fn, which for this problem is 0.25 times 12.5, which is 3.1 newtons. Okay, so it seems a little strange. You need 5 newtons to get it going, but once it's going, the force in the opposite direction is only 3.1 newtons. But you got to overcome that first. And the reason this is happening is because this guy is pulling up more, so it's reducing the normal force. The frictional force that you need to get it going depends on what the normal force is. So if you pull it up, you're reducing the normal force, you're going to reduce this number here. And that makes your friction needed to get it going a little less. And so this guy's pushing with enough to get it going. Once it starts to move, this is the frictional force. And then so once you know the frictional force, you can actually solve for the acceleration, etc.
Do we need to apply a force to push with a force that's bigger than the stationary friction so that it can move and we can reduce the force to equals to the inactive friction that we can move with the constant?
Right. All right, so I'm going to stop now. I'll stick around for a few minutes if you have questions. Tomorrow I'm going to do mostly this and more friction problems as well, so chapter 6 stuff.